Yeah, good afternoon, everybody. It's a real pleasure for me to be here. So, my first visit to Japan was to Sendai, and it's really a good opportunity to come back here, I guess after 18 years being the first time in Japan, and I always like to be here and discuss with you guys on magnets and new developments. And so I think this workshop is as well a good opportunity on bringing the community together on permanent magnets and maybe to advance the field a little bit. So what I'd like to talk to you today is about micromagnetic simulation of permanent magnets, and I'd like to show you how we can basically try to find good structures, good microstructures of a permanent magnet by computational design. So we use computer models to compute coercivity, energy density products, and remanence of a permanent magnet, and by changing the microstructure, we can find out how to improve a magnet's performance. So this work was performed at Danube University Krems, and I'd like to thank Alexander and Johan, two PhD students who contributed a lot to this work. Before going into detail, I'd like to thank our funding agencies. This is of course, the Austrian Science Fund, some European funding, but also very, very important, some funding from Japanese societies, the Japanese Science and Technology Agency, and also Toyota Corporation and Markham. And I'm really very glad to have this support to perform our research. So here's the outline of my talk. So at first, I'd like to give you a very short introduction on permanent magnets and how we compute magnetic properties. So this brings us to micromagnetics, and micromagnetics is basically a continuum theory to treat the magnetic properties, like the hysteresis phenomena. So we heard this very nice introductory lecture by Dr. Hirosawa in the morning, who showed us that probably for a full understanding, we need modeling over the full length scale, starting from ab initio simulations to spin dynamics and to larger size is micromagnetics. So here the focus will be on the larger size. So we'll talk about the influence of grains, grain shape, grain boundary phases, maybe also a mixture of phases, and see how this structure will influence the magnetic properties. This workshop is about composite magnets, and I'd like to focus on some of our results on nanocomposite magnets. And what I'd like to emphasize here is that by combining different magnetic phases, we can enhance the properties. And one important aspect is also that many of the soft magnetic phases we can mix with, for example, neodymium iron boron, have a very high magnetization and also a high magnetization at elevated temperature. So by maybe a clever combination of hard and soft magnets, we can improve the performance of a magnet at maybe the operating temperature of a motor. But speaking about high temperatures, we also have to take into account how thermal fluctuations influence the magnetic properties. And in the last part of my talk, I'd like to show you how we can treat thermal fluctuations in the numerical simulations. Now let's go back in history. So we are talking about composite magnets, and searching the history, this was the first example of a composite magnet I found. So around 1600, magnets were produced, like you see in the middle, this so-called Gilbert's armed magnet, and it's really a composite magnet. So we have two magnetic phases. So this ellipsoidal part in the middle is a lodestone, so a natural magnet, and there are these caps, and these caps are soft magnetic iron. So this is really a hard, soft magnetic combination, and in 1600, the people already realized that by inducing these soft caps on the magnet, you can enhance the flux and probably enhance the magnetic properties. So we move on in the centuries, and if you look at a neodymium ion boron magnet nowadays, you see that we have somehow more or less a similar structure. So at 1600, we had the lodestone and then an iron layer. And then we had lodestone and an iron layer. And nowadays, if you look at the unit cell of a neodymium ion boron magnet, we have like an iron layer, and then we have the rare earth layer, and then we have an iron layer, and then rare earth layer. And I think the reason behind is just similar. Like the rare earth gives us a high magnetocrystalline anisotropy, and the iron gives us a magnetic moment. And like in the old days, on a very different length scale, so the idea was the same. Before going into details of the simulations and like the design of magnets, let's see where magnets are used nowadays. So in addition to like transport, like hybrid and electric vehicles, a big driving force, at least in Europe and the US, is like energy production. Like there are a lot of windmills installed in Europe over the recent years. And if you look, you need about 600 kilograms of neodymium ion boron magnets per megawatt. And so if you install this big, for example, offshore windmills, we need a lot of permanent magnets. And so improving, for example, the energy density of these magnets, you can make these constructions much lighter. And so this is like a big driving force also to improve like the permanent magnets. Let's see what other fields are there where like high performance permanent magnets are used. So this graph shows you the usage of permanent magnets in the year 2015 in the different fields. So the units here like in thousands of tons, and we see that the wind turbines are basically the top usage of permanent magnets, and then after the windmills, there are already the hard disk drives, and the motor on the hard disk drive. Even though this is a very small amount of magnet per drive, the number of disk drives sold like leads to this about 7,000 tons of neodymium ion boron magnets used by hard drives. But there are also other fields, like I already mentioned, the hybrid and electric cars, which are almost the same usage. But then in all the consumer electronics, there are these acoustic transducers, there's air conditioning, and in transport, there are the electric pipes. And interestingly, all these like modern applications of permanent magnets, they have almost the same share of usage per year. And I think the predictions are that like both wind turbines and hybrid and electric cars like will rise over the next like 2 or 3 years. On the hard disk drives, that will probably go down over the next years. But still there is a big demand, especially for this energy conversion, energy generation on permanent magnets. If we design a permanent magnet on a computer, we need to think about a figure of merit. And one of these figures of merit, which is very important, is the energy density product. So if we look at a permanent magnet, we can measure the hysteresis loop of a permanent magnet. So we measure the magnetization as function of the applied fields. This is what you see on the left-hand side. And instead of magnetization as function of field, we can also plot the magnetic induction of a function of the applied field. Plotting the magnetic induction as function of field has the one advantage that the product of induction times field gives us some energy, and this like orange square I plotted here is basically the energy that can be reversibly used in a magnetic circuit. And this energy we want to increase, and so our effort is how can we design a permanent magnet so that the energy density product is maximized? And looking at this graph, we already see that the higher the remanent magnetization, the higher will be the energy density product. So it's a law that goes with the magnetization squared. So even a tiny improvement of the magnetization will give us some improvement of the energy density product. So energy density product goes with magnetization squared. But we need a certain amount of coercivity. And in order to get this maximum value of the energy density product, the coercive field should be at least half of the remanence. And for practical applications, probably it should be even much more than the half of the remanence. So what do we do now in order to address like the computational design of permanent magnets? So we are interested in the macroscopic properties you see on the top. So we want to maximize the coercivity, we want to maximize the remanence. This will give us a very good energy density product. And there are two ingredients that determine these macroscopic properties. On the one hand side, these are the intrinsic magnetic properties, like the magnetization, the magnetocrystalline anisotropy, or the exchange constant. So these are basically given by the chemical composition, the magnetic phase we have. On the other side, we have the physical and chemical structure of the magnet. This is the grain size, the grain shape, the boundary phases, the mixture of phases. And the combination and the interplay between the intrinsic properties and the structure of the magnet, this is what determines the macroscopic properties. Normally, it is easy, or not so easy, but we can talk with people who do experiments, and they will let us know what is the magnetization, what is the anisotropy, what is the exchange constant by magnetic measurements. Analyzing the influence of the structure of the magnet is a little bit more complicated. You need some transmission electron microscopy analysis, and you probably have to compare different samples. But what we can do is we can create structures of the magnets on the computer and compute like the hysteresis loop if we have the input from the intrinsic magnetic properties. The computation in magnetic materials is nothing which is very recent. So what you see here is like a computer which is probably almost 100 years old. And this computer was used by Stoner on computing this famous hysteresis loop you know from the Stoner-Wolfert paper for randomly oriented isotropic single domain particles. So this was a mechanical computer, and you could like integrate over this very complex integrals in order to evaluate the hysteresis loop. Nowadays, we are lucky, we have much bigger computers, we have parallel machines. But in the end, we do probably the very same. We minimize the total energy of the system. Let's see what can be done now in computational magnetism nowadays. So as we learned already this morning, there are different types of simulations that can be done. So there are atomistic and ab initio simulations, which are on a very small length scale. So we are on the length scales of atoms or electrons. If we compute like the intrinsic magnetic properties, like the anisotropy constant, we are in the length scale of like unit cell or grain boundary phase. If we do spin dynamics, it's again an atomistic model. And if we go up in the length scales, we are in the length scale of nanometers to micrometers if we apply the continuum theory of micromagnetics. There are also time scales involved. We probably are in the range of like less than picoseconds if we are on the atomistic model. We are in the range of like nanoseconds if we look at micromagnetics. But for our practical applications, we have time scales of seconds, minutes, hours, like in a motor, and we are on a much larger length scale, so we are on a centimeter length scale, or even bigger, so we use finite element modeling of magnetic motors, of magnetic circuits. And if we are interested in like thermal demagnetization over the lifetime of a magnet, or over like operating times, like of hours or days or years, then we are on a different time scale, and probably we need different means like kinetic Monte Carlo models in order to address this numerically. Let's go back to the length scales and look at the length scales that are given or imposed in the magnetic materials by its intrinsic magnetic properties. So the plot on the left-hand side was taken by Kronmüller's book, and he showed what happens like if I force my magnetic moments to rotate out locally, like if I have a local perturbation which is fixed, and then let's see how this perturbation of the magnet spreads into like a spin deviation. And we see that even if we like locally perturbate our magnetic moments, the spread in the spin deviation is much larger, and this distance here is like the characteristic length scales. And we have different characteristic length scales which can be computed by the ratio of the exchange energy over some other energy. And this ratio, the square root of this ratio is either the exchange length or the Bloch parameter you see here in the bottom. And the rule of the exchange energy is like basically a smoothing out of a local perturbation. And the rule of the other energy is basically what provides this perturbation. And for example, in neodymium iron boron, these characteristic length scales are around 2 nanometers. So based on this idea that like the exchange energy will basically smooth out what happens in a permanent magnet, there was the idea of the so-called exchange spring permanent magnets, like in the late 80s, early 90s of last century. And the idea was, if you combine like some soft magnetic material with a very high magnetization with a hard magnetic material which has like a high magnetocrystalline anisotropy, you may be able to improve the total magnetic properties or the energy density product of a magnet. We already talked about the Stoner and Wolfert hysteresis loop. So this is shown for an isotropic magnet here in red. And if you replace some of the particles with soft magnetic particles, and if you introduce an exchange coupling between the particles, you might get something which is the orange hysteresis loop on the right-hand side. And you see that we drastically can increase the remanence, which is good because high remanence means high energy density product. So this is a slide I showed like when it was the first time in Sendai, but I think it's also valid today. So this is a schematics how these nanocomposite magnets work. So for example, we have a combination of neodymium iron boron grains strongly exchange coupled with alpha iron grains. And if I apply a strong magnetic field, all magnetic moments are pointing up. So the hard magnetic grains might not be perfectly oriented, or they might be even randomly oriented. So these double arrows here basically give the anisotropy direction of the hard magnetic grains. If I now switch off my external field, then the magnetic moment in the hard magnetic grains will rotate parallel to the easy axis. But because these grains are exchange coupled and the exchange interaction smoothes out like local deviations, like in between the two hard magnetic grains, which are pointing like this, the soft magnetic grain is still pointing up towards the original saturation direction, and we have a much higher remanence. If we now apply a negative field, then the soft magnetic moments rotate out of the alignment direction, and eventually the soft magnetic grains fully reverse, and by exchange coupling also the neighboring hard magnetic grains will reverse. So based on this idea, we can make permanent magnets with a very small granular structure where we have a mixture of different phases like neodymium iron boron, hard magnetic grains, alpha iron, and also iron 3 boron as soft magnetic grains. So this is a transmission electron microscopy image by my former supervisor Joseph Fiedler, and on the right-hand side you see a corresponding micromagnetic simulations, which basically shows the domain structure in zero applied field. So in blue we have the alpha iron grains, in red we have the neodymium iron boron grains, and the white arrows gives you the magnetization, and you show that we see that we have a complex structure where basically we minimize the total energy. If you compare this with an electron holography image of the domain structure, we see that we both in the simulation and in the experiments we have very, very similar inhomogeneous magnetization, but overall we have a lot of magnetic moments pointing up towards the original saturation direction. How do we do these simulations? So we use the finite, thank you very much, we use the finite element method. So what we do is we take our microstructure, which was generated on the computer, maybe by some Voronoi type constructions of cells. Then we introduce a grain boundary phase, and both the grain boundary phase and the grains are subdivided into tetrahedrons. On each tetrahedron, we interpolate the magnetization vectors, and then we minimize the total energy of the system. So we start with a huge applied field, so we saturate the magnet, we minimize the energy, and get the stable equilibrium configuration. From this stable equilibrium configuration, we decrease the field, calculate the minimum energy state again, and we do so, and we basically follow the demagnetization curve. Using finite elements, we can be quite flexible in the shape of our grains, in the intergranular structure. So basically, we try to mimic realistic microstructures, maybe taken from electron microscopy images on the one hand side. On the other hand side, we can propose structures which will lead to excellent magnetic properties. So let's pick out one tetrahedron of this microstructure, and on this one tetrahedron we define magnetization vectors on the four corners of the tetrahedron. And if we know the magnetization vectors on these four corners of the tetrahedron by linear interpolation, we know the magnetization everywhere in space. Once we know the magnetization everywhere in space, we can write down the total energy of the system. So the total energy is, for hard magnetic purposes, mostly composed of like four terms here. We have the exchange energy, the anisotropy energy, the magnetostatic energy, and the Zeeman energy in the external field. So all these energy terms here are defined based on the unit vector of the magnetization, as you can see here. And the exchange energy upon minimization favors like parallel alignment of neighboring spins. The magnetocrystalline anisotropy energy favors certain crystallographic directions. And if we want to minimize the magnetostatic energy, like the magnet eventually will break up into magnetic domains in order to minimize the magnetostatic energy. And then we have the external field, and basically minimizing the Zeeman energy rotates the magnetization towards the external field direction. Now we put all these four energy terms together, and like different energy terms want to do different things, different directions with the magnetization, and it's this mutual interaction of all these energy terms which determines like a magnetic state. But by using our computational tools, we can find magnetic energy state for every applied field. There's one complication for somebody of you who wants to move into micromagnetics and doing research by computation. Up on minimization, we have to make sure in our algorithm that minimizes the energy that the norm of our magnetization vector always remains unity. So how do we do this energy minimization? So for those of you who have been at the Intermark conference like a few weeks ago, it was in Ireland. Ireland is quite a hilly like landscape, and if you have the chance to like go outside Dublin and drive through the nice landscape, you probably see what it means to minimize the energy. You start somewhere maybe on like a pass on the top of the mountain, and you want to find a way downhill to the next village or so. And we basically do the same numerically on a computer. Instead of this two-dimensional energy landscape, we have a very high-dimensional energy landscape. But we do the same as like here. Here you basically follow the road, and in the computation, we compute the energy gradient, and based on the energy gradient, we decide which direction we go down, and we follow towards the minimum. So what do? We start with an initial guess, and then we do like an iterative algorithm. We compute the energy gradient. Based on the energy gradient, we compute a certain so-called search direction, the direction we use to go downhill. Then we minimize our total energy in the search direction, and then we have a new solution vector, and we do this process again and again until we cannot go further downhill. So, which means that the energy gradient is 0. In the beginning of my talk, I showed you some computational results for isotropic nanocomposite permanent magnets. Of course, if you find some way to make a combination of hard and soft material for like aligned magnets, you might even gain much better properties. And in in the following, I'd like to show you some ideas of aligned composite magnets. So the most simple composite material would be a core shell particles. And during this workshop, we already learned a lot in different talks about core shell particles. For example, you can have a core shell particle where the inner core is like, for example, alpha ion, and the outer shell is neodymium ion boron. And if the core diameter is 20 nanometers and the thickness of the shell is 4 nanometers of neodymium ion boron, then we get this demagnetization curve, which looks very promising. So we have a coercivity of 2 Tesla, we have a like high magnetization. So this here is a normalized magnetization, so don't be worried, it's more than 1 Tesla. And we can observe also how the magnetization will reverse if we apply a magnetic field by our micromagnetic simulations. And this is what is shown here. So we have these points here marked on the demagnetization curve, and the pictures on the right-hand side shows you what's going on during magnetization reversal. So we see that first the magnetization starts to rotate in the soft magnetic core, and it almost reverses completely, and then a kind of domain wall forms between the core and the hard magnetic shell. And at some stage, the energy in this domain wall becomes just too high, and we can minimize the energy by also reversing like the hard magnetic shell around the soft magnetic core. Let's see how this looks like. So magnetization rotates, and then it takes some while, like the domain wall, you see the spins fluctuating a little bit here in the domain wall, and then the reverse domain expands into the hard magnetic shell. So once again, here the reversal stops, and then the domain wall basically is pushed into the hard magnetic shell. Now, the advantage of simulations is that we can play around with the properties. So for example, we can keep the shell thickness of the hard magnetic shell 4 nanometer and then change the diameter of the soft magnetic core. And then you immediately see that the higher the diameter of the soft magnetic core, the lower is the coercive field. But we also see that we drastically increase the remanence of the magnet. And then it's more or less a design issue, like how much of the soft magnetic phase you want to include, depending on what coercivity and what remanence you need in the design for your magnet. We can also play with the strength of the coupling between the core and the shell. So we can introduce a small layer of an intermediate phase, and in this intermediate phase, we can change the exchange coupling constant. And on the left-hand side, you see what happens if, like, the hard and the soft phase are weakly coupled. Then we reverse the soft phase, and nothing happens during this reversal with the hard phase, and we get this hysteresis loop like this. Now, if we increase the strength of the coupling between the hard and the soft phase, we see the soft phase reversal, but because now hard and soft phase are more strongly coupled, the hard phase coercivity also is reduced. And on the right-hand side, you see what happens if we fully couple the hard and the soft phase. So the message from this slide is that maybe in order to tweak and tune the coercivity of a nanocomposite magnet, it might be worth also to look at the strengths of the coupling between the two phases. So far, we looked at core shell particles where the soft magnetic phase was inside, so the core was soft and the shell was hard. You could wonder, okay, we can do it the other way around. So we can use like a hard magnetic core and a soft magnetic shell. The question is, which of the two like possible designs would give you the better properties? So either we have a soft magnetic core and a hard magnetic shell, or we have a soft magnetic shell and a hard magnetic core. And the answer to this question is, it depends on the volume fraction of the soft magnetic phase. So if the volume fraction is around 30%, then the soft magnetic shell will give you the better magnetic properties. And the soft core sees like this decrease of the magnetization at lower field. But if you want to increase the volume fraction of the soft magnetic phase, which normally is good in order to increase like the remanence, then you see that magnets that have the soft magnetic phase in the center, in the core, gives the better properties. So it depends a little bit, so the microstructure depends on how much soft magnetic phase you want to include in the magnet. So based on these considerations, we looked into a design where we embed soft magnetic spheres within like a hard magnetic matrix. So we have a hard magnetic cube of neodymium ion boron, and in this cube we place spheres of alpha ion. We can do so with various different volume fractions of like the soft magnetic phases, and if we have a low volume fraction, like the arrangement of the spheres is not so much important, but if we want to have like a high volume fraction of the soft magnetic phase, we have to go to a more like regular arrangement in order to increase the volume fraction of the soft magnetic spheres in the hard magnetic matrix. And then for each of these designs, we can change the diameter of the sphere, and we can look at the different volume fraction. And we can make a plot like this, where we have the energy density product as function of the volume fraction of alpha ion and as function of the diameter of the soft magnetic inclusions. Okay, in this case, the result is not so much like unexpected. So, of course, the higher the ion content, the volume fraction of alpha ion, the higher is the energy density product. And we see that the lower the size of the soft magnetic inclusion, also the higher is the energy density product. For these numbers here, we took into account, so we corrected this value here, taking into account like maybe the misalignment you will have in a real magnet, also maybe some non-magnetic phases, and also maybe some thermal spin waves I will talk about later. So from this slide we know, okay, the smaller the soft magnetic inclusions, the better for the magnet, and of course we can go to very high like volume fraction of alpha ion in order to increase the energy density product. Now the question is, like, hypothetically, if we have the possibility also to tweak the way we put the soft magnetic inclusions into our hard magnetic phase, does the arrangement of our soft inclusions have some influence on the magnetic properties? And so we did some micromagnetic simulations having like a soft magnetic inclusions in the red, and we have like a neodymium ion boron matrix. And in the one hand side, we basically form these chains of like soft magnetic inclusions, and in the other hand, like we have this lateral or perpendicular arrangement. And we compare the computed demagnetization curves, and we see that we can improve the coercivity by 4 Tesla here if we have this arrangement of our soft magnetic inclusions in terms of like these chains here. So why does this happen? Why is this better than this? We can look at what's going on with the magnetic flux inside the magnet during magnetization reversal. So the yellow lines here are the magnetic flux lines, and we plot the magnetic flux lines for different applied fields, and for the high fields, the magnet already reversed. And so this is for the perpendicular arrangement of our soft inclusions, and this is for the like aligned arrangement, vertical arrangement. And you see here that with this arrangement, we have something like a flux concentration, like from one soft magnetic inclusion to the next. And this flux concentration basically stabilizes the magnetization, and we need a much higher field in order to reverse the magnetization. So if we have the opportunity in designing a magnet somehow to put our soft magnetic inclusions at certain places, it would be good to use like these chains and not like this horizontal arrangement, because here we concentrate the flux and we improve the coercive field. So let's move to granular systems. So we already learned this morning about the microstructure of a permanent magnet. So we have the grains, we have a grain boundary phase, we might have a defect layer or just like a soft magnetic grain boundary phase. We have these triple junctions here. And now our idea was, okay, what happens if we take one of these grains of a neodymium ion boron magnet and we replace it like with a composite materials where we have like a hard magnetic phase and like some soft magnetic inclusions. And now we want to compute the potential of such a hypothetical magnet and see what magnetic properties we can achieve here. Again, let's look at the structure of like one of these grains here. So at the outer surface, we have either a defect or a soft magnetic grain boundary phase. Then we have a hard magnetic phase. Then we have soft magnetic inclusions. And of course, the interface between like the hard phase and the soft magnetic inclusion will not be sharp. So we have some interdiffusion layer here in white with some average properties between hard and soft magnetic phase. Using micromagnetics, we were interested in what is the optimal geometry here. So what are the optimal sizes of the soft inclusions and like the gap between the soft inclusions in order to get like the highest possible energy density product. And using computers, we can use some software for like numerical optimization. And the software basically computes the demagnetization curve, then the software evaluates some objective function, and then the software tells us, how do we have to change our design parameters in order to improve the energy density product? And if we go this circle many times, we end up maybe with an optimal structure here. Possible design parameters we can imagine is like the size of the soft inclusion and like the distance between the soft inclusions. And the distance between the soft inclusions basically is how much of a hard magnetic layer we have between our soft phases. On the right-hand side, you see the result. So on this axis, we have the thickness of the hard magnetic layer between the soft inclusions. On this axis, we have the size of like the soft magnet, and like here we have like the energy density product. And you see that if the soft inclusions are too big, we lose energy density product drastically because we cannot establish a high enough coercive field. If the size of the soft phase is too small, we also lose energy density product. And there seems to be a maximum at the size of like the soft cubes of around 20 nanometers. And similar, if we look at the gap size between the soft inclusions here, so the thickness of the hard magnetic layer, we see that the thinner the hard magnetic layer, of course, the more volume fraction of soft phase we have. But if it becomes too thin, maybe we also like lose coercivity. And so from these simulations, we conclude that like a soft phase of about size of about 20 nanometer and like a hard magnetic layer in between the soft inclusions with a thickness of about 2.5 nanometers will maximize our energy density product. At the time when we did the simulations, I had a postdoc coming from England, and in England there is this famous sweet, this famous cake here, which is called Edinburgh cake. And then we thought, okay, that's how our proposed magnet structure looks like. And we proposed like the so-called Edinburgh structured magnet. And what we did is like for different hard-soft combinations, we computed like the remanence, the coercive field, and the energy density product. And we found that if you use this structure you have seen just before and like then cover the outer shell of this grain with the magnetic phase with the properties of the samarium iron nitride phase, then we can have very high energy density products even at 450 Kelvin. So by tuning the structures, at least theoretically, we can show very excellent hard magnetic properties also at elevated temperatures. Okay, let's look at the structure again. So we have like some soft inclusions, and we used iron cobalt as the soft magnetic phase. Then in between the soft inclusions, we have a thickness of around 4 nanometer of the hard magnetic phase. And the hard magnetic phase was neodymium iron boron. And then like this dark outer shell can be like a different magnet than neodymium iron boron, for example, the samarium iron nitride. And then we should not forget that if we look for a granular structure, we probably have a soft magnetic grain boundary phase. So we have to take into account that maybe nucleation might also happen from like a soft magnetic grain boundary. So we can do our micromagnetic simulations for the structure here. And what you see here is the magnetic induction as function of the external field. And I included two curves here. So the dashed blue curve is what you would obtain with a classical micromagnetic simulation. So minimizing the total energy as function of the applied field and calculating the magnetic equilibrium states for every field point. However, we operate this magnet like maybe at 450 K, so there will be thermal fluctuations. Thermal fluctuations will have two effects. They will reduce the remanence. There will be long wavelength spin waves, so the magnetic vectors will fluctuate. And there will be a reduction of the coercive field because like the thermal fluctuations can drive the system over energy barriers. So if we carefully want to estimate what's going on with our properties, we have to include thermal fluctuations into the micromagnetic simulations. So let's start with the reduction of remanence, so this difference here. So what we can do is we can integrate the Landau-Lifshitz equation for a certain amount of time, and towards all the effective fields, we add a random thermal field. And due to these random thermal fields will kick the magnetization vectors because of the exchange between the magnetization vectors. There will be spin waves, and the wavelength of the spin waves is like maybe half of the grain size or the grain size, so it's related to the microstructure, the wave of the spin length. But the spin waves will reduce the magnetization, as you can see here on the right-hand side. So if we, for example, on a point here, so we have a reduction of the magnetization due to the external and demagnetizing field, and then we have a reduction of the magnetization due to spin waves. So let's have a further look. So here you see a slice through the magnet, so the red arrows indicate the direction of the magnetization in a classical micromagnetic picture. Now, if we switch on thermal fluctuations, we have these kicks of the magnetization vector, and you immediately see here that these images are changing like over a time scale less than a nanosecond. So we have spin waves, and the magnetization fluctuates. And if we take the average magnetization over a certain amount of time, then we reduce our magnetization from the dashed line to the red curve here. So with this Landau-Lifshitz approach, we can calculate this red curve until the point here, but we cannot compute the reversal step here, because this reversal happens over a much larger time scales than nanoseconds. So in order to compute this reduction of the coercive field, we have to use a different approach. So we have to look at the energy barrier between the state where all the magnetization vectors are still pointing up and between the state where number 3, where we already have reversed the magnetization. And in between the state 1 and the state 3, there is like an energy barrier. And if we compute the height of the energy barrier as function of the applied field, we will get this curve here. And the energy barrier will become 0, so we can switch the magnet at the coercive field. But now we have thermal fluctuations, so we don't have to wait until the energy barrier becomes 0. So we can use the thermal energy, for example, 25 kPt, to overcome the energy barrier here. And so our coercive field now is not the line where the energy barrier becomes 0, but our coercive field is the line where the energy barrier as function of field crosses the 25 kPt line. And by this means we can compute like what happens at finite temperature with our coercive field, and you see here that this reduces the coercive field a little bit. So how do we compute these energy barriers? We use a method which was well established in chemical physics. This is the so-called string method. And the string methods gives us the minimum energy path like over a saddle point. And this is a path which is most likely to be followed by a system if we go from an energy minimum over a saddle point to the next energy minimum. And like if you compute reaction rates in chemistry, this is a very well-established method in order to like compute the height of energy barriers, and we do nothing else like applying this method in micromagnetics. So by this method, we get the so-called minimum energy path, and this minimum energy path tells us what's going on from a minimum towards the saddle point, and then how reversal will happen. So we will see how reverse domains form and expand in the magnet. So if we do so for our hard, soft composite magnet, we will see that we will form a reversed droplet of magnetization, maybe somehow like in a soft magnetic inclusion. So this is before the saddle point. So if we then go up in the energy, so these reversed droplets will expand, and at like the saddle point, you see that we already have 2 of these droplets. And then like if there's this 25 kPt of thermal energy, we can overcome the saddle point, and like these 2 droplets merge and expand, and the magnet will reverse. So with this, I come to the end of my talk. So here's a short summary. We've seen that at least theoretically, it's possible to design nanocomposite magnets that have very high and attractive energy products at 450 Kelvin. If we look at the prerequisites to achieve such good magnets, we need soft inclusions with a size of around 20 nanometer, and the distance between the soft inclusions, the thickness of the hard phase in the optimal case is around 2.5 nanometer. Thank you for your attention.